So folks, we saw this previously, the subspaces of R3. So if we think about R3 as a vector space, we can talk about its subspaces. And it has subspaces. All of R3 is considered a subspace. So I don't know how we want to depict that. We're talking about the entire space here, all of R3. And then it also has as subspaces the collection of all planes passing through the origin. Those are subspaces of R3. So planes passing through the origin. The other subspaces of R3 are all of the lines passing through the origin. And then there's the trivial subspace, which is just the point 0, which is itself a subspace. Why? Because it's closed under scalar multiplication and vector addition if it's only the vector 0. So it's kind of a silly subspace to talk about, but the subspace that just has the vector 0 itself is a subspace. Now we're going to need this fact. This may not be in your notes if it's not, just add it down. That for a linear transformation, then the image of T is a subspace of, so let's just think about this, what we're saying here. So we've got this vector space V here, some amorphous space, and we've got this vector space W here, and we have a transformation that takes all of this space and maps it to some part, maybe all of it, maybe not, of this space. So we call this, and let me do that in a different color. We call this red space here the image of the transformation. So it's all the vectors in W that had vectors in V mapped to them. That's the image of this transformation. So this image, first of all, let's just say that it lives in W. And what I'm claiming here is that it is itself a subspace, and we can prove that, or have proved that in class. Okay, putting all these facts together, I now want to look at a sequence of transformations. So this first transformation here, I'm thinking about this right here as my matrix A. So we've got T mapping from what space to what space. Well, this is going to take vectors in R5 and map them to vectors in R3. I want you to think about that for just a second. This is a 3 by 5 matrix. And so what types of vectors, column vectors, can I multiply to this? I can multiply it to these 5 by 1 column vectors, and it will return a 3 by 1 column vector. So that fits with what we said in the previous videos. So the question is now, what does this look like? Well, we can't draw a picture of this, right? I can maybe draw this amorphous blob to represent all of R5, but I can't actually draw a picture of it. I can, however, in this case, draw R3, and we can think of our transformation as taking all of the vectors in R5 to some place in R3. Well, we just said in the previous number 6 here that the subspaces of R3 are all of R3, the planes passing through the origin, lines passing through the origin, or the trivial subspace. And because the image of this transformation, this mapping T here, which is going to take the vectors in R5 to the vectors in R3, because the image of this, all the vectors that get something mapped to them from R5, has to be a subspace in the domain space here, then I know that it's going to be one of these 1, 2, 3, 4 potential subspaces of R3. This would be more complicated to do in higher dimensions, but the analysis sort of still fits. What I've done for you is I've row reduced this matrix A here. So this is our matrix A that does the same thing as the transformation. So another way to think about it is it's going to take some vector X in here, and it's going to map it to some vector Y sitting here by saying that AX is equal to Y. By doing the left-hand multiplication of matrix A to the vector X, that gives us this vector Y, which is this vector in R3. Well, what types of vectors, let's ask that question, what types of vectors in R3 get vectors in R5 mapped to them. So what vectors and we can answer that question simply by saying, let's solve the matrix equation AX equals B for some vector B in R3. And let's be a little more concrete about this. Let's just pick any old vector in R3. So let's pick, I don't know, say the vector 3, 2, 1 living in R3. And we're going to ask the question, what vector in R5 gets mapped? We're asking the question, what vector in R5, if any, gets mapped to this particular vector in R3? And all we would need to do to figure that out is to solve this system. Here I'm going to copy down our matrix of 1, 2, and so all we need to do is we need to solve this equation right here. And if this equation has a solution for this vector in R5, then we know that the vector 3, 2, 1 has some vector in R5, at least one, perhaps infinitely many, but at least one that gets mapped to it if this has a solution. And what I've done for you is I've given you this matrix here in RREF form. And so here's the crux of this, and this will allow us to go through the remaining problems a lot faster. If I try to solve this equation right here, for this arbitrary vector 3, 2, 1 that I picked from B3, there's a solution, and we know there's going to be a solution because when we did the row-reduced echelon form of our transformation matrix, it has 3 pivot columns. 3 pivot columns was the most it could have, and we do in fact have 3 pivot columns. And so that tells me that any vector B sitting in R3 has, in fact, has at least one vector in R5, perhaps infinitely many, that get mapped to it. And so that means that this transformation takes all of R5 and maps it to the entirety of R3. That's the image of this transformation. It's all of R3. So that was a little bit tedious. Let's get to another example very quickly. So again, here we're going to take all of R5 and we're going to think about there being some transformation T that's going to take me to R3 somehow. And we can think about which vectors in R3 have the vectors from R5 mapped to them. So again, what we'd be doing is if I were to label this matrix as A, is I'd be asking the question AX equals B. Picking any B here, is there a solution to this? Careful, this B, remember, in this case is in my range space, my image space, and X here is in R5. So by solving this equation right here, we're going to answer the question, is there a vector X sitting here in the domain space that gets mapped to this particular vector B right here living in the range space? If this system has a solution, then yes, there's some vector in the domain space that gets mapped there. Well, in this case, I've put this matrix again into RREF form, and we can see that we have 2 pivot vectors. We could have at most 3. We ended up with 2 pivot vectors. That means that these that the image of this transformation is some plane in R3. That's our image of this transformation. So this was again the same size matrix. This was a 3 by 5 matrix just as before, but this particular 3 by 5 matrix morphs all of R5 space into this plane that sits inside of R3. We could then go find exactly what that plane looks like by solving this system of equations abstractly. Finishing this out, let's do 2 more quick examples. So again, we're asking the question, I can't draw R5, so I'll just draw this sort of blob, but we know that we've got this transformation that's going to take me to R3, and the transformation is this matrix A here, however I choose to label that. Usually we use A. So this is our matrix A here. And again, we know that it's a 3 by 5 matrix, so it's going to take us from R5 to R3. And it's going, you can think of taking this space and morphing it. Folks, I know that that's a little abstract. That's why we did this first example here. That's why we did this first example here previously, where we thought about taking R3 and mapping it to R2, where you can actually see the vectors in R3 and you can see where they land in R2. And now we're doing this for a lot of different cases for these vectors in R5. And so the question is how does this space get morphed into R3? And the answer comes through looking at this matrix in its row-reduced form. We see that we have one pivot column, and that's going to correspond to this entire R5 space getting mapped to this set of vectors right here. This would be the image of the transformation T, this set of vectors right here that lie along this line. So maybe this vector right here, this vector x1, it gets mapped to this position right here. That would be A sub x1. Let me take that line out. That would be a little confusing. And maybe this, let's see, let's pick a different color. Maybe this vector x2 right here, maybe it gets mapped right here. There's where A of x2 lines up. But all of the 5-dimensional vectors in R5 get mapped to vectors that lie along this line right here in R3. And we can see that by this pivot column. So in this case, we have sort of a boring example of a transformation where we're going to take all of R5, and where is it going to get mapped to? Well, its range space we do think of as being R3. This is our range space here, and this transformation T, which behaves by taking a vector, say x right here, and mapping it to, so it gets mapped to, well, AX in the range space, but in this case, where will it get mapped to? When I take any vector and multiply it, so if you think about this matrix right here, A, if you were to take A times vector X, it's going to map it to the 0 vectors. Careful, folks, there's a couple 0 vectors here. This is the 0 vector 0, 0, 0. That's the 0 vector in R3. And in fact, all vectors, I could take some other vector, let's give it a different name here, maybe just call this one U, it would get mapped to 0 as well. All vectors in the R5 space are getting mapped to the point, to the 0 vector in our R3 here. Folks, this was kind of a longer example, but I hope this helped to clarify, looking at how in each case I had a linear transformation. Why? Because we have a matrix for its representation. And in each case, this linear transformation was mapping us from R5 to R3, but each one was slightly different, and that was determined by the number of pivot columns that we were looking at here. If you have any questions about this is going to take a little while to digest. That's okay, but I wanted to show this to you now. But if you have any questions on this, let me know. Otherwise, I'll see you in the next video.